Exam 3, here it is. Convert the behavior of the following Verilog module into a truth table. I'm pretty proud of this question because this really sort of gets at the heart of what it means to synthesize HDL. This module has a 3-bit input A and a 2-bit output Y. So there's a couple ways you could do this. You could see we've got A bit 2, sorry. A bit 2, A bit 1, A bit 0, and it should be lowercase a. And then we've got outputs are Y bit 1, Y bit 0. Okay, so probably the easiest way is to just put there's 3 inputs, so there's 8 rows in this table. So 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Put some horizontal lines. Okay, so keep the current color scheme. Okay. So if bit 2 of A is 1, which covers the bottom 4 rows, then the output is 1, 1. So 1, 1, 1, 1, 1, 1, 1, 1. If A bit 1 is a 1, which covers these 2 rows, then the output is 0, 1. And that just leaves the else, which is going to take A bits 0 and 1 and assign those to the outputs, like that. Any questions? Now some of you put don't cares on the table to reduce the number of rows you had to write out. That's fine, that's no problem. But this is a fully enumerated version. Any questions? Okay, question 2. Write a system Verilog module named minority. If it receives 3 1-bit inputs, A, B, and C, it produces 1 1-bit output Y that is true if at least 2 of the inputs are false. There's many ways you could do this. This would be behavioral Verilog. So module minority input logic. Oh, so you got A, B, and C. A, B, and C. Output logic Y. Semicolon. So if statement, always at star with or always comb with an if statement or an assign. I use an always comb. Always underscore comb. Do we need a begin? Probably not. I could just do it with one if statement. If not A receives, it produces if at least 2 of the inputs are false, right? Yeah, not A and not B. Right, those are two possibilities. Sorry, that's and. And ampersand. Sorry, it's drawing a blank there. Ampersand is A, right? And if A and not B, or not B and not C, or not A and not C. Make sense? If that's the case, then we say Y equals 1 apostrophe B 1. Else Y equals 1 apostrophe B 0. And then end module. End module. No semicolon. That should do it. Any questions? Okay. Yeah, so I don't think we were too tough with the syntax here. You could also do this with an assign statement with a trinary operator. You could do it with a, I don't know if you could do it with a case, probably. Be a nested case statement or something. You could also do it through, actually, you could probably just do it through, you don't even need an if, actually. You could just say y equals this expression, right? Because in Verilog, if you have a conditional statement and a conditional expression that evaluates to true or false, that is equivalent to a 1-bit true or false, right? So you could literally just say assign y and then this. That works too. Okay, any questions about that? Okay. All right, so that was the behavioral Verilog, and then the next question, I believe, oh, actually, the next question says write a self-checking test bench, right? So this one, module test bench. Okay, so test benches have they have first of all no inputs and outputs. They're self-contained. So module test bench semicolon. There is a this is a combinational circuit, right? So we don't need a clock or a reset, right? Because it's combinational. If we were writing a test bench for a sequential circuit like a state machine, then we'd need to generate a clock or reset. So for this, we need to have some internal signals to connect, and we need to actually instantiate our design under test. Our design under test is the minority module, minority dot, I'm going to call it dot design under test, and it's going to have a dot A, dot B, dot C, dot Y. I didn't fill in the actual connections yet. That just sets it up. And then I need to have some wires, so I'll just have logic A, B, C, and Y declared here. And so I'll just fill those in, A, B, C, and Y. Right? So I've got my design under test. I've got wires connected to it. So now I just have to drive them and then check their output. So for that, I can use an initial block. Begin. And then, does it say test every? It says we don't need to have a test vector file, but test every possible value. So this is going to be a little long, but we want to say A equals 1B0, B equals 1B0, C equals 1B0, and then we need a wait. So put a little delay in there, and then we need an if statement that says if y doesn't equal, what should it equal? Well, remember, y is true whenever at least one of the inputs is true. In this case, all three of them are true, so certainly y should be a 1. Probably could just say if y, but instead of y, if y, if I could have said if not y. But the point here is that I have an expected value of y, and I want to check it against the actual value of y. So the expected value is 1, the actual is called y. So if y doesn't meet my expectations, then I will display an error. And you don't have to do anything fancy here, just error. Normally you would print some more informative message about maybe the time that the error took place or what the inputs were when the error happened, but it wasn't required for this problem. Just wanted to just display error, right? And then you just, let's see, we can change C now. So C was 0, I'm going to toggle it to 1 and put my delay in. And I'll say if y doesn't equal, again, y should be, the expected value of y is 1 because A and B are still 0, C is 1, so minority is still the output is still true, and then display error, and so on and so on. So I won't go through all 8 combinations, but that's the first 2. Any questions about that? Okay. All right. Next. Write module name majority. It has X, Y, and Z. It produces an output A that is true if at least two of the inputs are true. It must instantiate minority. Okay, so this is the inverse of minority, right? So module majority inputs logic X, Y, Z, X, Y, Z, output logic A. And then we have to instantiate minority, so minority foo. And then I'm going to connect A to X, B to Y, C to Z, and Y to A. Okay. Now in this case, I don't need to declare any internal signals because I can use all of my top-level I/O can connect into that minority instantiation.
Don't need to invert the output?
Yes, I still need to do that. Oh yes, yeah, that's correct. Yeah, I still need to do that. You're right. So it's a good point. So I need to. How can I do that? Well, I could create an internal one for that. So I'll call this B, and then logic B, and then I can say assign B equals not. Assign A rather. Assign A is not B. There you go. Yep. There you go. Thank you. Yeah. I think if there's another way to. I don't know if there's an easier way to do that. But yeah, in this case, I do need to have that. I need that internal signals to do the inversion. The end module. Good. Any questions? Yes?
Could you just invert the inputs?
Could do that too. I wonder if you could. Yeah, I was thinking that's a good point. You could probably invert the inputs here, in which case you could then just connect the output directly to A. Right? Makes sense? Because the problem is that I don't think you can put. I think here you can put not X, not Y, and not Z because they're inputs. But you can't put not A here because it's an output. Right? I've never tried to. I assume you can't do that. I've never tried to do that. You guys with me? Make sense? So you can invert the input before, sending them in. But if you want to invert the output, you'd have to do it as a signal. So in that case, I wouldn't need those two lines. All right, great. Next question. What's the purpose of the sensitivity list in a system Verilog always statement? The sensitivity list acts as the sort of like the inputs to an always, but whenever any of the states of any of the signals in the sensitivity list change, that triggers the evaluation of the always block, or the always statement. Block if you have a begin and end, and there's a block, but if it's the always, I should say always statement. You guys with me? Okay. Number 4, blocking assignments update values immediately. Non-blocking assignments update the assigned value after all other actions associated with the current event have completed. How many clock cycles of delay will the code below impose between the input inval and the output D? I think this was probably the one that was most confusing. The idea is that this was designed to follow the example from the book, where the book introduces this. This always _FF is going to trigger once a cycle, right, on the rising edge of the clock. But when it does trigger, the inval will transfer into A, and then that assignment will take effect immediately, meaning that on the next line of code, A transfers to B, right, and then B is non-blocking, which means that B is B. This next line of code will still see the old B. You guys with me? So what this means is that this first statement is kind of redundant. This is equivalent to just saying it's equivalent to taking the inval and substituting that for A. Like you could take this A and make it inval. It's like saying inval goes into B, right? And that creates a flip-flop behavior, right? So that puts a 1 cycle delay on B. Excuse me a second. Okay? Everyone with me? So that's a 1 cycle delay. And then the next time we trigger this, we'll have the new input of B. So the B will be updated on the next cycle, which then gets transferred into C, and then that C gets updated right away. So that B substitutes in for C. So that's equivalent to saying B or D gets B. You guys with me? So that'll add another cycle of delay. You guys with me? So if you synthesize this, you would get a circuit that is comprised of 2 flip-flops connected in series. The input would be inval. The output of the first flip-flop would be A, but it would also be B, right? So this wire in between would be both A and B, right? Because they would be equivalent. And then the output of the second flip-flop would be both C and D. All right, so this forms this shift register. It's going to take us 1 cycle to propagate inval to A, and a second cycle to propagate A to D, or I should say B to D, whichever one we choose, right? The point of this is that when you use the blocking assignment statements, it makes A equivalent to B and C equivalent to D. Okay, any questions? Okay, it's confusing, but at the same time, it's really important in Verilog. This comes up a lot, so it's important that you understand that if you're writing in Verilog. Okay, sketch the state transition diagram for the FSM described by the following system Verilog code. This one you have to do in stages. You have to first look and check out what states we've got. Look, there's 4 of them as defined by this enumerated type, state type, and they're called S0, S1, S2, and S3. So you can start with just putting those down. S0, S1, S2, S3, doesn't really matter where you put them. Just kind of get the... Okay, S0 is the reset state. That's usually, because if reset is 1, we're going to assign the current state to S0. So that's usually denoted by a little triangle that shows that. You don't have to show anything on the state diagram that denotes that it's the positive edge of the clock. So this first always statement is the clock logic. Then we've got the next state logic. It says that if our current state is S0 and A XOR B, then go to S1. So there's a state transition from there, which is A XOR B, which is true when you have a 0, 1 or a 1, 0. Notice the arrow, I don't know if the arrowhead is really clear. There's an arrowhead there. Otherwise, the next state is S0. So there's a loop back here if I've got a 0, 0 or a 1, 1. If I'm in S1 and I've got A and B is true, meaning that A and B are both 1, then I go to S2. Otherwise, I go to S0. So if I have a 0, 0, 0, 1, or a 1, 0. And S2, A or B, I go to S3. So 0, 1, 1, 0, or 1, 1. Otherwise, I go to S0, which would only happen on a 0, 0. And finally, S3, if A or B, then I stay in S3, 0, 1, 1, 0, or 1, 1. Otherwise, I go back to S0, which would happen if I get a 0, 0. That's it. Kind of looks a lot of crossing lines, but that's it. Any questions? Yes? Good? Good? Okay. Sketch the hardware that the following system Verilog module implies. This was a little tricky because there's an always underscore flip-flop, and there's two statements in there. This creates two flip-flops. There's only one always statement, but there's two flip-flops that it implies, corresponding to each of those two lines. So we've got a flip-flop here, a flip-flop here. The first one outputs Y. This other one outputs X. And Y is X or C. So Y is X or C. And X, the next X is A and B. So like that. Yeah, you should have clocks here too. Technically. A lot of times those are left out though. For example, when you took 212 and you looked at all the diagrams in the 212 textbook, they didn't, I think they usually didn't show the clock.
I only asked because
Okay.
I had the clocks and didn't have the flip-flops. I couldn't pay attention to the list at the time. Or, yeah.
Okay. Okay. No, but you're right though. In reality, there does have to be a clock connected to the flip-flops. And that's it. Okay, great. Any questions? That's the exam. Okay, good. All right, so now let's continue on with chapter 5. So we've learned about combinational logic, which you already knew from 211, then sequential logic, and then hardware description language. The next step is to start working towards more complex designs, larger designs. Specifically, in this book, they're working towards the design of a CPU. We want to build a CPU, sort of from the bottom up. So the next step in that process is working our way up one level of abstraction to digital building blocks, the basic components that make up a CPU. We want to build them with things that we already have. So examples of that are, well, we already know gates and multiplexers, decoders, registers we've got, arithmetic circuits, we haven't talked about that yet, counters, memory arrays, logic arrays. So some of those things we've covered already and others we haven't. The first topic is adders. We've talked about full adders before, and I think you covered this in 211. A full adder is a building block for a larger adder. Full adder is basically a 1-bit adder. So A and B come in, they're both 1 bit. Then you have a carry in and a carry out and a sum. So it's like adding 3 1-bit inputs together and producing a 2-bit binary output. So if all 3 of these are 1, then my carry out is 1 and my sum is 1, indicating a 3, right? You guys remember that. And I think in 211 you probably also covered ripple carry adders, which is where you can build an arbitrary size adder by chaining together full adders, linking each one's carry out to the next one's carry in. These are often called columns because when you add, you generally line up your two values you want to add, you line them up. and this is A, and this is B. So you line them up with their corresponding bits. So the least significant bit, rightmost bit, bit 0 is lined up there on the rightmost column. So you line these bits up in columns, right? And then the carry-ins would, be up top. So 1 plus 0 is 1, no carry in to the next column. This would be a 1 with no carry in, but now I've got 1 plus 1 is a 0 with a carry out of 1, and a 0 with a carry out of 1, right? So these are your carry outs, and this is the sum, right? Everyone with me? Okay, so that's the column terminology. It doesn't look like columns on this diagram, but if you do like that you can see there's columns. Okay, so the problem is that there is a critical path here that starts with carry in and continues all the way through the circuit. So the delay of this adder is simple to calculate. It's just the number of bits n times the delay of a single full adder, right? So this is too slow. So no one uses full adders. There's this thing called a Carry-Lookahead adder, which is a solution to this, where you calculate a generate and a propagate bit for each column. And the generate bit, so if we look at this example again, notice how this column here, I was adding a 1 plus a 1. That is going to guarantee a carryout no matter what happened before that in the columns to the right of that. So that's called a generate. This column, 1 plus 1, will generate a carry, that carry, no matter what happened before it, whether there's a carry in or not. On the other hand, this column, this leftmost column, was a 0 and a 1, and it has a propagate in the sense that if I hadn't been carrying something in, I wouldn't have got a carry out. But because I carried into that column from the previous column, I got a carry out. So it will propagate a carry. If it gets a carry in, it'll propagate the carry into its carry out. But it won't create a new carry out regardless. Right? You guys with me? Make sense? Right? So that's generate and propagate. It's actually, they're simple to calculate because the generate for column n is just simply the A and B n. Right? The only way to get a generate is if both my inputs are 1. Right? Likewise, propagate is also very simple. It's just A or B. Right? Now, what's the point of creating yet another output in each column? It's because with generates and propagates, if I'm a column, I can figure out whether I'm going to have a carry in based on the generates and the propagates of the columns to my right. Well, to its right. The bits, the columns of less significance. You guys with me? So the way that works is that let's call this is column 3, right? So the carry in CI3 is going to be the generate of column 2, which is exactly what happened here. Column 2 generated a carry that went directly into column 3. You guys with me? You know what I'm talking about when I say 3? Starts at 0 on the right, 3 is to the left. Right? Or I could have had a propagate on 2 and a generate on 1. Or I could have had a propagate on 2 and a propagate on 1. Now that's the weird thing here, is that the propagates, you could propagate across multiple columns. And a generate on 0. Or I could have had a propagate on 2, propagate on 1, propagate on 0, and a top level carry in. So now I've just calculated, I've looked ahead. I didn't wait for the carry to ripple to me. I figured it out ahead of time based on the generates and the propagates of each bit. Now you might say, wait a second, that's a lot of stuff there. That's huge. Yeah, but this is only 2 gate delays. Well, plus the 1 gate delay. These guys are 1 gate delay each to calculate, and that's 2. So, in principle, of course that assumes that I can have arbitrary size gates, but in principle, in 3 gate delays, I can figure out my carry-in. It's pretty good. The problem is, of course, that doesn't scale arbitrarily high. So, usually the way it works is you generate propagates and generates for groups of bits, for ranges. So you can actually, instead of individual bits, I can generate whether this entire block of 4 bits will generate or propagate based on its internal generate and propagates. You guys with me? What does that mean? Well, the whole thing, basically, if all the propagate bits inside this block are all 1s, then the whole thing propagates, right? So in other words, generate 3 down to 0 is the leftmost generate, or the leftmost propagate, and whether you carry into bit 3, column 3. You guys with me? So this kind of nests itself down, right? Make sense? So this way, I have to generate, now this is where things get a little overwhelming. So let me step back here a minute. You've got a group of 4 bits. Each one of those bits will generate a sum bit, right? Do I still generate carryouts? Like, do I still do this? No, you don't need to anymore, because I'm looking ahead to generate these, right? So technically, my full adders now just have to generate this sum, right? And then but then I also have to add a G and a P to each column, right? Which was not shown in that first truth table. Okay, that's fine. So I've got a G and a P, and then from those I can generate a G and a P for each block of 4 bits, which I do this way, right? You guys see that? So propagate is like, if all the propagates are set, I'll propagate all the way through all 4 bits. Generate is a little bit more complicated because it depends on if I have a generate inside the group of 4 bits and propagates out to its left, then I'll generate out, right? Okay? Okay, so what that gives you is something that looks like this. You've got 4-bit blocks. So this is a 32-bit adder here, but it's decomposed into groups of 4 bits each, so 8 groups of 4 bits. Each group of 4 bits generates 4 bits of sum just directly from the full adders, right? Inside there. And then the carries internally aren't shown here, right? But you could actually do ripple carry adders inside these groups of 4, or you could do carry look ahead if you want to. But frankly, it doesn't really matter because there's not a huge difference between ripple carry and carry look ahead within a group of 4 bits. But what's important is that you generate, actually, they show it here. Here they're showing it as generating the individual, so this is a carry look ahead internally. Well, no, actually, no, they don't show that. I'm sorry. They generate the propagate and generates internally, but then the purpose of this circuit is to generate to create the G, the 4-bit generate and the 4-bit propagate here. You guys see that? Right? So this big group of gates here is the generate for the 4 bits, and of course the propagate is just an AND gate, a 4-input AND gate. You guys with me? Okay. All right. So then from this, we can figure out what the carry out is. This guy. Based on these guys and the carry in coming into this block. Right? Now you might say, wait a second, hold on. Wait. You're saying it's using carry in now? Yeah, it does. It's still using carry in. So in a way, you still have to ripple the carry in through each block of 4 bits. You guys seeing that, right? Because technically this carry 3 is calculated relative to this carry in. This carry 7 is calculated with respect to this carry 3, but then that carry 3 is calculated with respect ultimately to the carry in. So we still have a rippling going on, but it only ripples across every block of 4 adders instead of every single bit. You guys with me? So what that means is the delay for this circuit is the number of bits, n, divided by k, which is the block size that you chose, which it was 4 for that example. You guys with me? So what this basically means is it's still kind of a ripple carry adder, but you only have to ripple 8 hops, right? So it's 32 divided by 4. Well, minus 1. 32 divided by 4, so 7 hops. And that, now here's the other neat thing about this. Notice that the carry in, this is very subtle, but notice that the carry in doesn't experience the same delay through this circuit as these guys on the right-hand side. The carry in only goes through this last little piece. You guys with me? So things are actually even better because I only have to go through it. Well, I shouldn't say better, because if it was a ripple carry, you'd still only go through 2 gate delays. But the point is this carry in is only experiencing 7 delays, but it's only multiplied by the propagation delay for that and or, right? Okay, so what's the total? The total delay is the time to generate the propagate and generates, the single bit ones, right? That's one gate delay. That's not a big deal. And then you add the delay for the propagate generate block, which is the block that generates all of the block level, not the single column, but the block level P's and G's. And you might say, wait, why do you add those? Well, you have to add them because you have to get the single bit P and G's before you can get the 4-bit P and G's. So that's along one logic path, so you have to add those. Then you have to add, because you're doing this for the whole adder, you're going to have to multiply that, in this case, 7 times, you have to go 7 hops through the and or gates, which is 7 times through this guy. To go from bink, 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 bink. Well, it does 7 because it does 7 instead of 8 because I guess it assumes that we don't need that final carry out. Right? Because there'd be 8 blocks. You have to go through 8, right? Yeah, you'd have to go through 8. So if you wanted the final carry out, this guy, it would be 8. So it depends. So technically it shouldn't be. I think I kind of I disagree with this because this really should not have a -1 if we want the final carry out, which a lot of comparator circuits require that final carry out. If you're comparing the values of 2 values and you're subtracting to figure that out, so you might want that final carry out. Also, a lot of chips store that carry out in a flag register. Anyway, so that's not a big deal. But the point is you divide the delay by 4. And then KTFA, you have to add the delay of all the full adders. Why? Because that's K, so this is the block. Right? So in other words, the reason you have to, in order to get the sum bits for each block, you need the carry in, right? So that's along that path, right? So I need to have the carry in order to calculate the sum for each block of 4. Everyone with me? That's pretty straightforward, I think. It's a lot of pieces to it, but okay. So now it turns out, and to be honest, I didn't actually know about this until this semester. But this is really cool. There's a third kind of adder. It's even better. It's called a prefix adder. This one is even faster than the Carry-Lookahead. So the idea with this one is that we want to calculate, again, it's based on propagates and generates. The premise of it is that instead of doing like this guy does, where you still have this ripple effect from right to left, the prefix adder calculates the carry-ins in a way that looks like a tree, a binary tree. The way it does that is, there's a few basic observations. Let's see, column, okay, so a couple things. So start out, column -1 is the carry-in, right? That's the column that's to the right of the rightmost column. They're going to rename that generate -1. Because it makes sense, right? They have to establish the notation to build this thing up, okay? So the top level carry-in is generate -1, and the top level, and the propagate -1 is 0. Everyone see that? Makes sense? Okay, then the carry-in to column I is the carry out of column I -1. So they establish this relationship, which is the carry-in to C -1 is the generate to I -1, meaning the generate of the column to its right all the way down to -1. You guys with me? So this is a little bit different because in this case, instead of calculating, one of the differences here is instead of calculating the carry-ins explicitly, I just calculate these generates of the column to my right. So it's based on this idea that if I know the generate to my column to my right, then I don't have to worry about, I'll just treat that as my carry-in. You guys it make sense? Okay? I don't want to have to worry about propagates when I'm calculating my carry-in. I only use the generate of the column to my right. Okay? So the idea is that they generate these, or they calculate these generates on these prefixes. So notice that this is generate 0 down to -1, generate 1 down to -1, 2 down to -1, 3 down to -1, and so on, right? So this generates, so for each column, I can generate a sequence of prefixes that allows me to calculate my carry-in. Okay, so let's see. Yeah, so block I down to J will generate a carry-in, a carry, if the upper part, so you've got I to J, and this is decomposed into two halves. There's I to J is the whole range. Then you've got I to K, which is the top part, like the left part, and K -1 down to J is the right part, right? So the idea is that you have a, you take like for example, in this case, I've got two columns here and two columns here. So if this guy over here was my I and this one was my J, I can decompose this into I colon K, where, for example, K could be 0, 1, 2, right? So this would be 3 down to 2, and this would be 2 down to 0. Oh, sorry, 1 down to 0, right? 1 down to 0, because it's K -1 down to J. You guys with me? So that's how I've got this guy decomposed. So the idea is that if the right half generates and the left half propagates, then I'll generate from this block of 4. But if the left half generates, and I don't care what the right half does, the whole thing generates. Okay? All right. So from that, you can decompose into this binary tree where you start out and you look at each pair of inputs, right? Each pair of columns, rather. So 0 down to -1, 2 down to 1, 4 down to 3, 6 down to 5, 8 down to 7, and so on. And then once you've got those pairs, you can build up by taking, now this is a little bit hard to read, but what this is showing is that this, so I can pair together columns 2 and 1. They come together here in this black box. Then the output of that goes into this black box, and the other input into this black box comes from this pair that came to its right, right? So in other words, that gives me, I start out by looking at 2 down to 1 and 1 down to -1, right? So I get those two intermediate results, and then I go down one level, and I take the 2 down to 1, and I combine that with what I got from 0 down to -1. So it's a little confusing, but the notation they're using is, they actually violated their rules. Remember back in chapter 2, they said if you ever have a, oh no, I guess not. No, they don't need a no, they're good. They're being consistent. Yeah, so they have these two bits come down and join here. This guy gets this group as well as the output of this one over here. You see that? And so those two wires are not connected, but that T junction is. You guys see that? Right? So then from this, you start out with groups of 2, then groups of 4, then groups of 8, and then finally, once you get down to the bottom, like for example, 8's carry in can be calculated from, in this case, they get 7 down to -1, which is calculated from here. They get 6 down to -1 plus the 7, right? So when you create these two halves, they don't have to be equal halves like I showed here. They can be unequal halves where the carry in to 7 can be calculated from, sorry, in this case 6 down to -1, which itself is 6 down to 3 and 2 down to -1. So I get an input from here and an input from here. Make sense? Okay. Right. So now you might be thinking here, like, how does that, each one of these boxes, what do these actually represent? Each of these black boxes gets 2 inputs, left and right. See, left, right, they all have 2 inputs. The one on the left is the generate input, right? So we're looking for, in this case, like I'm just going to randomly select this one here, 6 down to -1. I'm looking for the generate that comes out of here and the propagate that comes out of this guy, the 2 down to -1. Right? Make sense? So that's what each of these 2 inputs represents. And then it's like I said, it's confusing because you've got all these these line crossings here. But keep in mind that you only care about where the line starts. So this most significant box is getting the generate from 14 down to 7 and the propagate all the way over here from 6 down to -1. It comes all the way over here like that and goes in there. So my left group of bits that I get the generate from is 14 down to 7. The propagate group of bits is 6 down to -1. Oh, sorry. Yeah, right? Right. Yeah, so generate so the generate is the generate of I to k, that's the first part, plus the propagate of I to k and the generate of k minus 1 down to j. Yeah, sorry, I said that wrong actually. So you have to consider the generate, the left half of the generate and the left half of the propagate with the right hand side of the generate, right? Make sense? This one's confusing, I know, it's hard to explain. So let's look at this one of these ones up here. So I've got, these are column. This is a column. Now, by the way, these are columns, right? So when I say 2 and 1, this represents bits 2 and 1 of both inputs, right? So these are 2 columns, and from both of these columns, I can combine these together here to figure out the generate and the propagate values from these 2 columns, right? Right. In this case, it's pretty easy because it's really straightforward. What would this actually be? Well, the generate would be the generate from this column 2 would be what? It would be if A and B bits 2 are both 1, right? So that's what this input is I've got A bit 2, B bit 2. If they're both 1s, that would be a generate, right? The propagate would be if, for that same bit would be if either one of them are true, right? You guys with me? Does that make sense? I think that puts it in more concrete terms, right? If I can actually, so this box is looking at the generate and the propagate of the bit of column 2 and column 1, right? And from that you can build up as a tree. So the advantage of this is the delay is that this adder scales as a log base 2 of n. And let's confirm that. How many bits we got here? Well, there's 16 bits, 0 to 15, right? So this is a 16-bit. Now, don't get confused because this was a 32-bit adder here. That example is 32 bits. We jump ahead to this one is now 16 bits. So a 16-bit adder has to go through 4 levels of these prefix generators, right? So it's a log base 2 of 16. So I have to go through the 3 levels. So that's where you get log base 2 of n. And then you multiply that by the time of the black prefix cells, which makes sense, right? I have to go through 4 of those guys. 1, 2, 3, 4. Every one of these things goes through exactly 4, or not all of them, actually. That's the worst case is 4. Overall, like for example, getting down to these guys. Okay, any questions about that? All right, so to give you an idea, a ripple carry, so they calculated, this is for a 32-bit ripple carry adder. They have some gate delays, 2 input gate delay, 100 picoseconds, full adder delay, 300 picoseconds. For the carry-lookahead, they do 4-bit blocks. You could choose a different block size for that if you wanted to. That would be a good question for the exam, actually. Try to calculate this for, I don't know how much, see how to figure out how to structure that. But the numbers they got were 9.6 nanoseconds for the ripple carry, 3.3 for the carry-lookahead, which is like a third, and then another third for the prefix. So the prefix adder is lightning fast, right, for an adder, right? Okay, what kind of adders are actually used in a CPU? I don't know. I'm not sure about that. Depends on the CPU, I guess. And probably depends on the adder. There's adders all over the place, so it probably depends on which adder you're talking about. Any questions? Okay. How about subtractors? How do you make a subtractor? It's actually really easy. You say, you basically build it on top of an adder. So you say A minus B is equal to A plus minus B. Right? So you just negate B. How do you negate B? The 2's complement. You say A plus 2's complement means what? You negate B, or you complement all the bits of B, right? And you add 1. Right? But here's the problem. There's 2 adders here. Do we need 2 adders to make a subtractor? No. You can use the associative property of addition. The associative property says A plus not B. I could put parentheses around that and then add 1 like that. And thus I can just negate B, right? And then that final plus 1, I could use that as my carry in. So I just wire the carry in to 1, and that becomes a subtractor. Because every adder has a carry in, that little carry in then the first column, right? That when I first learned about adders, I'm like, why don't we just get rid of that? Like, why do we need that first carry in? Well, that's why you can't get rid of it, because you can use that to make a subtractor. How about comparators? If we have two values and we want to compare them, how can we do that? Well, the way they show it here is they use an XOR gate. So they put an XOR gate between each of the bits of the two inputs. And then, actually XNOR, right? There's a bubble there, right? It's an XNOR because you got the extra line there, which makes it an XOR, and the bubble makes it an XNOR, right? XNOR is true if both inputs are 0 or both inputs are 1. And so if all the outputs of those XORs are 1, that means all of the corresponding bits of A and B match up, so that means they're equal, right? Is there a better way to do that? Actually, you could just subtract them and check to see if the result is all zeros, right? Now you might say, wait a second, hold on, that's got to be worse, because look at this, is 2 gate delays. You're talking about subtracting, that's got to go through a full, you got to build like one of those big prefix adders or something, right? Or a carry-lookahead adder or something, or ripple carry, in which case it's really slow. This has got to be faster. Yeah, but see, this is this is deceptive, because if I have 32-bit values and I want to compare them, I need a 32 inputs on this AND gate. That's really slow, right? Because it turns out there is no such thing as a 32 input AND gate. It doesn't exist. You can't feasibly build it in CMOS logic. So what you'd have to do is replace this gate with a cascade, possibly a tree of AND gates here, right? But the point is that you'd end up going through many gate delays getting through this AND gate, depending on how big of a comparator you want to build. You guys with me? So there's a trade-off. Now, by the way, here's something that's kind of weird. In Verilog, what happens if you go to Verilog and you say assign out equals A equals B? And let's say these are out. Sorry, that doesn't look like a U. Out equals A equals B. How does this get synthesized? Does it get synthesized like this? Or is it going to get synthesized like a subtractor? I don't know. It's up to the synthesizer. That's why you would never do that, unless it was for really small A and B. See, no digital logic designer worth his salt would trust the Verilog compiler to decide how to implement this statement. Right? They'd probably design at a lower level, even in the Verilog. Design their own comparator without relying on Verilog's equals operator and how that'll treat and how that'll actually synthesize it. Right. Okay, how about less than? How do we know if A is less than B? We have two inputs, A and B. We want to know if one is less than the other. How do we determine that? This is something you might have talked about in, did you talk about this in 212? I used to teach this in 212 when I taught it. Does it give us the answer? Oh yeah, yeah, it does actually. You take A and B and you subtract them, right? And so now here's the problem though. This actually depends on whether A and B are signed or unsigned. So if you if A and B are both unsigned and you subtract, well, what is this showing? This is showing bit n minus 1, so that's the signed bit, right? There's n bits, A and B are both n bits. This is to subtract. And then they look at the sign. So they're saying if A minus B is negative, then A must have been less than B, right? Makes sense, right? But that works assuming they're signed numbers. This is a signed subtractor. Okay, so they've got this ALU. So if we were actually in the lab version of this class, we would actually be building this ALU in Verilog. But I'm just going to quickly take you through how you do it. Basically, you've got an ALU that is supposed to be able to do multiple functions. It's supposed to do multiple things to A and B. So you put A and B in, and you want to be able to tell it what you want it to do with A and B. Add, subtract, compare, or do a shift, or do some sort of bitwise logical operation. So this is the basic building block of a CPU, right? It's kind of like a calculator, sort of. You give it two numbers, and then you give it an operand. You tell it what you want it to do with those two numbers, and it'll spit that out. You guys with me? Okay? So this is kind of like the top-level block diagram. A and B are both n bits. Y is n bits, which could be 32 or 64, depending on what your native word size is on your CPU. And then you've got this, in this case, a 3-bit function code, which will define what you want to do with A and B. You guys with me? So if I put a 0, 1, 0, it means I want to add. So you have this table. Now you might want to say, where's this table come from? How do you establish this? Well, there's a reasoning for that. There's a couple conveniences they build into this that lead into this encoding, but we'll get to that here in a second. Oh, looks like I'm just about out of time now. Okay, well, good. We will pick up here on Monday, because we have no class on Wednesday because we'll be off for Thanksgiving. Then we'll have just 2 more weeks left. We'll have 2 more quizzes, and then we'll have our final exam.